let's get started. So my name is Julian Hyde. I'm a PMC member of Calcite. I work for Google. And today I'd like to talk about adding spatial capabilities via Calcite. The reason it's interesting is Calcite is predominantly a relational system, and spatial data has a very different feel than relational data. And there's a reason that there are specialized geospatial databases, because the data looks different, it's handled differently, and it benefits from a different physical organization in order to be able to process queries. But there's also a lot of good stuff about the relational model. Let's start off with an example of a spatial query. So let's assume we're in a latitude, longitude grid, and so we're looking at a set of restaurants, each of which has a location. I'm in location 6-7, the yellow circle in the top right, and I'm interested in restaurants within 1.5 kilometers of me. And as you can see, there's 2 restaurants that fall into that. So PostGIS and some other GIS extensions are actually an extension to the SQL standard, and several databases, including PostGIS, implement those. And Calcite does too. So that's how you'd express this query using SQL with GIS extensions. So basically, it's a set of functions, all of which are prefixed st underscore, and we're saying we're looking at the restaurants table. We're creating a point out of the x and y columns in the restaurants table, and we're making a point out of a point object from our current location 6,7. Then we apply the distance function and say, is the distance between those 2 points less than 1.5? And that works. It gives us the right answer. The problem is that it's slow. The simple way of implementing it basically forces us to retrieve every row from the restaurants table, apply the function to it, and check the result. And if the restaurants table has millions of rows, that's a lot of extra calculations. And that's, as you know, that's not the way databases work. The way databases work is to kind of look at the predicates and narrow down to a particular subset of the table. But the way we initially implemented these functions in Calcite is to simply use Esri's geometry library and just provide a simple row at a time implementation. So the challenging part is to move from that row at a time implementation to a more efficient implementation. And that's kind of the subject of this talk. So going back to that dynamic between the kind of the design tension between spatial databases and relational databases, what do relational databases do really well? They're very good at the predominant data organization techniques are sorting the data and partitioning it, and perhaps sorting it organized by a hash function. So an example of what I'd call a vanilla database is Apache HBase, which it divides the data up into a number of region servers. And each region server has a particular range of key values. And within the region server, each table is basically sorted. So there are many other databases that have that. And even if you think of a regular relational database such as Oracle or Postgres, the tables aren't sorted, but they have indexes on them. And an index is basically a table that is sorted by key. So whenever I'm talking about sorted tables, you can also imagine that this applies to conventional B-tree indexes as well. So when the data is stored in sorted order, you can also do range queries. And at the bottom of the screen are three examples of range queries. So just looking at one particular point in the key, like name equals king yen. Looking at 2 points is the second query, and then you can have a set of ranges. So and in the last query, I'm looking for 1 point, but I'm also looking at a range, everything from SA to SZ. That's a range scan within the server, and also saying the name is null is, you can think of a null as one of the allowable values of name, and therefore that's putting those conditions together. That's still a range scan that basically gives the table scan a set of values in the allowable range of names. Then the last thing that relational databases do extremely well is algebraic query rewrite. In Stamatis' talk, he was talking about using optimizer rules. That's what I'm talking about here, is starting off with relational expressions, transforming them to equivalent but cheaper algebraic expressions. So how do we bring these things into to handle spatial queries? I just wanted to mention search arguments, which is something that I added last year, which allows you to allows us to represent ranges in a more uniform way, and also allows us to optimize them better. So on the right, we've got 3 different predicates, but they are all actually equivalent. So first of all, you can express it using between and in operators, but then we can expand that into basically an OR of simple less than, greater than, equal to conditions. So we've expanded the top one into the middle one. And then lastly, we introduce a search argument. It's a constant value that contains a set of ranges. You can think of it as a generalization of a bitmap. If you have an integer column and you want to say 1 through 5 and 10 through 20, well, you can represent that as a bitmap, 1, 3, 5, 10, 11, 12, and so forth. But bitmaps only work for integers. SOGs work for all data types that have a less than operator. And so it represents a set of ranges within that data type. And that if that data type has an infinite number of values, then the range can match a potentially infinite number of values. But it tends to be a very concise expression. It's a constant expression. And we can do things like combining SOG expressions during the optimization process. So we can intersect them and union them and so forth. And the whole reason we're interested in SOGs is they are easily implemented by a scan of a sorted table. So why do these techniques not work for spatial data? If you've decided to physically organize your data in a sorted fashion by creating a B-tree index, or organize your data by hashing, then the problem with spatial data is when you access that data, you have to do a scan over your data in sorted order. And if the data is two-dimensional, then 2 restaurants that are very close together in real life, perhaps they have identical x coordinates but different y coordinates, are going to be basically stored in very different places in the disk. And in order to reach all restaurants in a particular locality, you're going to be looking at a lot of different regions of the disk. So restaurants that are physically close to each other in 2 dimensions are going to be a long way apart on the disk. And this just means that an efficient implementation, if the data is organized in that way, is simply impossible. So the problem is this dimensionality. Two-dimensional or 3-dimensional or 20-dimensional data just has a different, cannot be laid out with good locality. And so we need to reduce the dimensionality, convert it into a 1-dimensional data set, so that we can cluster the data, so that data that is near in real life is also near in the disk. There are two ways of organizing data. And this, this is throughout the geospatial literature. You can have data-oriented data structures and space-oriented data structures. And I'm just going to give an example for what these are. So let's look at a spatially skewed data set. This is actually you can imagine this is every restaurant in the United States. It's actually from the US Census. This is represents the population of the United States. And you can see that it's skewed, that there are very few people living in the Great Basin in Nevada, Utah. And most of the US population is basically in the east part of the country. So if we use a data-oriented data structure, and an Archery is the kind of classic example of that, implemented in many geospatial databases. You basically divide, the Archery self-balances itself, so there's an equal amount of data in both sides of the tree. So when you're constructing an Archery, the first thing you do is you divide the data in half by the x-coordinate. And then you divide the data in half according to the y-coordinate. And as you can see, the dividing line, the horizontal dividing line, is not exactly the same. And we continue this process, dividing the data into this binary tree, first slicing on x-coordinate, then slicing on y-coordinate. And we end up with a set of smaller and smaller squares, but because the tree is approximately balanced, the number of points in each of these cells is equivalent. So this is a balanced tree, and the number of levels is double what it would in a normal tree, because we're dealing in 2 dimensions. But it's not that deep a tree, and it's a pretty efficient data structure. The problem is that it's a specialized data structure, specialized for geospatial data, and a lot of databases, and it's difficult to maintain transactionally, and a lot of databases just don't have an Archery implementation. So instead, the other approach is to say, don't look at the data, just look at the space. In other words, let's look at the values that latitude and longitude can have. And this is much simpler, because you just say, okay, I'm just going to create a grid. Now these squares are not of equal size. There are many more restaurants in, let's say, the New Jersey, New York area than there are in around Salt Lake City and Reno. But it's simpler, and we are actually going to choose. We're actually going to use the grid data structure because it is something, because the arrangement of the grid is known at query planning time. You don't have to consult, you don't have to look at a data structure which is going to change during the running of the database. It's predictable, and we can do the rewrite at query planning time. And this is a design trade-off, but it turns out that it's not that serious a design trade-off. The last technique we're going to use is a concept for mathematics called a space filling curve. So a space filling curve is a line that travels through an n-dimensional space. In this case, it's a 2-dimensional square. And it's one single line that covers every point in the two-dimensional space. It's kind of amazing that it's even possible. And we create it, it's a kind of a fractal. But as you can see on the right-hand side, we've got a square, an 8x8 square, and the line is of length 64. And therefore, every point in the square has a value between 1 and 64. And a very interesting and important property of this curve, there are other space filling curves that have similar properties. A very interesting property is that if 2 points are close together in x and y coordinates in the plane, then they are likely, it's not for certain, but they're likely to be close together on the curve. And therefore we've achieved what we wanted, which is to create some locality. So let's go back to that spatial query before, where we're using the ST distance function to find all restaurants that are 1.5 kilometers from the point 6,7. And we're going to apply this Hilbert index, or this Hilbert curve, and we've added a value, a column H to the table, which is the distance of the point along this Hilbert curve. And we know that all restaurants that are within 1.5 kilometers of 6,7 are going to be on a particular range of the Hilbert curve. And we can represent that range as H between 35 and 42, or between 46 and 46. So, and we've modified the query, and we've added this extra range to the where clause. Now, the range is approximate. There are some restaurants that lie on that curve that are maybe 1.6 or 1.7 kilometers from our location. But it still eliminates an awful lot of the negatives, and it allows us to find all the restaurants we want, and and perhaps a few false positives, by simply just scanning a range or a couple of ranges of the table. So by changing the formulation of this query, we're giving a strong hint to the database that a range scan is possible. And by the way, this condition here is what we referred to earlier as a SOG. It's a range set. So how do we tell the optimizer to do this? First of all, we add this column, and we make it a generated column, which means that when records are inserted into the table, their values are automatically populated. And we tell the optimizer that this column does always have this value, ST Hilbert X, Y. We also physically sort the table by H, so that when we do a scan of the table, we're going to read, record 36, Station Burger at 36, and then the next record we read will be King Yen with the H value of 41. So this is simply a sorted table. This is exactly the way you'd store data in HBase. And then using this information, the fact that there's this H column, we can do an algebraic rewrite. And there's a rule in Calcite called the filter Hilbert rule that looks for a filter relational expression that calls the ST distance function, and it converts into a filter that applies this SOG condition, $search, applied to a particular SOG. That SOG is generated from the point and the distance at planning time. So it converts it into this filter, which is more complex, but still more efficient because it's working on a smaller set of data. There are many variations on this theme. So there are many patterns, ways in OpenGIS that you can express this query, and they basically all mean the same thing. And Calcite recognizes quite a few of them, and we can add more if there's other ways that people conventionally frame these questions. And there are other query patterns that can also use Hilbert functions. So, for example, checking whether a point within it is within a particular polygon. So we used a circle previously, but you can check within polygons, and those can also benefit from using the Hilbert functions. There are other kinds of spatial queries which can't use Hilbert functions as such, but can use the same kind of techniques we've been talking about, that is relational query rewrite. So for example, I'm at this particular point, the yellow circle. What state am I in? So I'm trying to join between one point and a set of polygons which are stored on disk. I'm interested in a polygon which represents the Yellowstone National Park, and I'm interested in intersecting it with a set of all states to find out which states overlap Yellowstone. Which national park intersects with the most states? So I'm interested in the set of polygons that represent national parks, the polygons that represent states, intersecting them, or in fact joining them, and then doing a sort limit. So here are some of the ways that you'd represent those queries. So for those things, we can't, because we're joining essentially polygons to polygons rather than a constant point to a polygon, there's a technique which is dividing the space up into tiles. So we basically create this tiling grid. And for example, the state of, well, let's look at tile 8. So tile 8 contains pieces of Montana and also pieces of Wyoming. So we can use that tile index to very quickly find, looking at my current point, I know that by simple arithmetic that I'm in tile 8, and then I can use this index to tell me which states intersect tile 8, which should be a small number of states, and therefore I'm just reading. I'll then do a quick check to find out whether my current location is within the boundaries of the state of Montana or within the boundaries of the state of Wyoming. Materialized views are another of these, another technique from relational database that we bring in here. A materialized view is a relational expression. It's the association between a table that exists in the database and a relational expression of which is what the optimizer knows that table contains. And the reason materialized views are interesting is if you have a particular query and the optimizer knows about a materialized view that contains a subset of that data, then the optimizer is empowered to rewrite to use that table. So this example here is a classic summary table that you might use in business intelligence. It's a table that contains a group by. But as we'll see, you can have materialized views that contain spatial expressions. So here we are going to build a tile index. So we've got this set of states. We have this function called stMakeGrid that given a geometry, so for example, the state of Montana, will basically break up the state of Montana into a set of regions that fall within the particular tiles. So for Montana, MakeGrid returns for each geometry, for each state that it's given, it returns a collection of geometries, each of which is sliced along the grid boundaries. And the way we've chosen the granularity of these tiles, each state is basically going to be decomposed into 2 or 3 tile fragments. And we store this materialized view. We store that as a physical table, and we store it sorted, sorted by tile ID. So that's the table that we saw a couple of slides ago. And the optimizer now knows that table exists, and it can use it if it wants to help execute queries. So let's look at that. Which state am I in? We've basically added this, automatically added this in clause, state ID in the set of states in the tiles table where tile ID equals 8, because I know that my current point is in tile 8. And then we keep the intersects check, which was in the original query, to deal with the any false positives that might have crept in. So here's that process represented as a algebraic rewrite. We're looking for a call to intersects with a constant point. And we're also relying on the existence of a materialized view that is built, that contains the tiles. And then lastly, we require that that table is physically sorted on no, not sorted on the state ID. We require that the states table is unique because we don't want to introduce duplicates. So if we match that pattern, a filter on intersects, we apply the tile semi-join rule, and it creates a semi-join to the tiles table. So just to recap, traditional relational databases use storage techniques such as sort and hash, which just don't work on higher dimensional data. And therefore, implementing spatial in a relational database requires us to make some tough choices about whether we use specialized data structures such as archeries or general purpose data structures. And the approach we're describing here is using general purpose data structures, which allows us to create a general purpose database that can handle not just spatial data, but also financial data, also business intelligence, also things like streaming. Perhaps you'll want other kinds of data mixed into that database, like, for example, document-oriented data. So the relational algebra allows us to use general purpose data structures and general purpose algorithms and nevertheless deliver spatial data. That's all I have. Thank you for listening. I think there's time for a couple of questions.
Thanks, Julian. It was a great presentation. So in the QA section, I don't see somebody with questions. Ah, here comes one. Can you see it, Julian? Serg asks, could be the similar approach with Hilbert functions for 3 dimensions?
Yeah, absolutely. Yeah, space filling curves. Hilbert function does work for any number of dimensions. There's also a curve called a Z curve that's heavily used. Yeah, they all generalize. I think if you get to a very large number of dimensions, if you're dealing with, for example, some ways of analyzing, for example, document similarity, they use like, thousands of dimensions. I think that the space filling curve approach begins to run out of road if you have more than, let's say, 4 or 5 dimensions. But certainly for 3-dimensional data, including height, or perhaps 4-dimensional data, which would be temporal plus spatial, then the Hilbert functions and approach would, I think, work pretty well.